My dear students, in the last lecture we discussed the quotient group, its properties, some problems. Now today we start the very important topics of group theory is group homomorphisms. So let us start with the definition of a group. We take generally we take two different group. One is the binary operation of star, and another is a G1. Another binary operation is dot O, and then we have to define a map from G star to G1 with this binary operation, and then we can say that it satisfies this condition as for all A, B are the element of a G. And now clearly we have a this is the we have a set G, and this is our we have a G1. There is a we have a define a map F in a such a way where we have a this is X and so on. We have some elements of Y. Somewhere we have an element of a this is equal to we have a X star Y, and then we have to the element of a this is equal to the f of x, and so on, and there is a sum of the element of this f of x star y, and then we have a f of b is there. So this means we can simply say that under the operation of this preserve this mapping. So let's start the formal definition of the binary of the group homomorphism. Let G with the binary operation is star and G with the binary operation dot O be any two groups, and phi be a function from G into G1 and denoted by phi is equal to G to G1, then phi is said to be homomorphism, or we can say the operation preserving function, because this preserves the operation of a function. This is the in the element of a G, because G is a group, then X composition Y preserve operation into G, and these are the elements of you have a G dash because you have a map is this is say map is G to G1. If you have a X is the element of here, then this should be map in the form of a psi of X, and then similarly you have a Y is mapped into the form of a psi of a Y. If we have a X and Y are the element of a G, then clearly X is a group, so X composition Y is also the element of a G in this case. And then similarly we have a because G prime is also a group, so we have to this X is the element of a G1, then this is Y is also the element of a G1, and in this case we can say that this X under the binary operation of a G1 this also set, and then this preserve binary operation here, this preserve binary, and then we have to just the psi of this X composition operation preserving is the same as a psi of a X into Y. So just simply we say that we have two groups of a binary operation. G is on one binary operation, G1 is another binary operation, and we have a one function, and this function from G to G1 is then this function is said to be homomorphism, or we also called as a operation preserving function from G into G dash if and only if every pair of x y is satisfy this condition. So phi of x, so X composition Y is equal to phi of X into phi of Y. This is the operation of this G1, and this is the operation of a G2, G and G1. You just say that in the we have to write in the form of this f of X star Y is equal to by the homo preserving this the form of X, and this is equal to we have a psi of Y. So this is the left hand side is a product of this is a computed into the G. This is the element of a G, and now see this right hand sides you have to just say that you have a again I just write and this is equal to Y. So while the right hand side product this is calculated into a this is the element of a G, and this complete product into the element of a G1. So, the functions described in this definition possess the characteristic property and carrying the product into the product, and then we have to say that the simplest image of this we can represent it in the form of this x. I take a y, then this is mapping to this. This is you have a map as a, this is the function of a, you have a psi, and then x is mapping to phi x. X composition y should map in the form of a psi x composition of a psi y, and this is equal to y is the phi of y is there. So, this means we can simply say that this is the figure. We can say that this preserving the operations into this is called as a homomorphism. So, we just take a as a trivial example. You not just that we are taking as a any function identity function, we denote it as a ig is equal to x. Now, this is clearly is a function of this. We have to travel I function is defined from G to G, and G is any group under the binary operation is star. So, we can take any two elements of this. X composition y is the element of a G for all x and y is the element of a G. So, we can write in the form of this ig of x composition y is the same as a x composition y, but we define ig is equal to identity function. So, this is x composition y because the this map is defined from G to G. So, both the operation binary operation are the same. So, this means ig function is this. This means the we can simply say that a trivial example of a homomorphism, but an important one is the identity function. Identity function is always is a homomorphism for any arbitrary group under the binary operation and defined in the form of this form. So, this means we can say that this is clearly is a homomorphism. So, this now this is a very trivial examples of a homomorphism. Suppose G is with the binary operation this, and G is two groups with the identity elements E1 and E2 respectively, means we have this E is the identity element of a G and E1 is the identity of a G1, and this is the G is a group under this binary operation, this group in the this binary operation. Now, we have to just define in the form of this. So, you have a psi is a map from G to G1, and then you can just say, we can just say psi of x is maps to identity of this G, means we have to for all x is the element of a G. This is very important. I just later on we have to discuss this form. So, this is you have a psi, and then you have some elements of x, y, and so on, and then here you have some elements are there, and then after that is some identity element of this is denoted by A. Is saying that phi x is equal to identity, x1 is equal to identity, and so on. For all x, these are the mapping to the this identity element. Now, if all the elements depend identity element, then we have to take a x composition y is equal to, this means if all the elements map to I, then you can clearly say that x and y are if are the element of a G, then x composition y is also the element of a G. By the definition, we can say that phi of x composition y is also is equal to E1, and now you know that E1 is the identity of a G1. If E1 is the identity of a G1, then E1 can be written as a E1 binary operation E1. So, this can be written as a E1 binary operation of E1, and E1 is equal to, we can say that we have a phi of x, and then you have a psi of y is there. So, clearly we can say that if we have to take two groups with the identity elements E and EG respectively, and then we can write this psi of xy is equal to E. So, this is a clearly satisfy this preserving the this mapping. So, we can say that is also satisfy the homomorphism condition is there, and in this particular mapping is the only constant function satisfy our definition, and this is the particular called is a trivial homomorphism, is also called is a trivial homomorphism, because we have to all the elements mapped to the identity element of the other groups, and then this clearly is a satisfy this definitions condition, and then clearly we can say that this is a is called is a trivial homomorphism in this case. So now we just take a another example. I take a, let us consider Z is under group addition and G is equal to 2 to the power n, and this is G is a 2 to the power n is equal to, this means you can say that 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power minus 1, 2 to the power minus 2, and so on. These are the group of a G, and we take a G is this form, and then we have to clearly this is a group under multiplication. So this is a group under multiplication. So we just take a map from Z to this, and then we have to define as a phi of n is equal to 2 to the power n. Now we have to check if this is a homomorphism or not. So we take for checking the homomorphism, that means we have to verify the condition of a homomorphism. That condition is you have to take any two elements, m and n is the element of a integer. Then by the mapping we can say that phi of m is equal to 2 to the power m, phi of n is equal to 2 to the power n, and also we know that if m and this, so you have a m plus n is also the element of a z. So if you take a map of phi of m plus n, then by this property this can be written as a 2 to the power m plus n, and now by the property of this 2 to the power m and 2 to the power n, and now 2 to the power m is you have a phi of m, and 2 to the power n you have a phi of n. That means we can say that this is nothing but is equal to phi of m plus n can be written in the form of a phi of m into phi of n under multiplications. So this is again preserving. This means clearly this map defined from Z to G is clearly is a homomorphism. So this the one of the example where we say that this is clearly is a homomorphism our case. Okay, now some more examples we have to take a this is trivial, and now I just take a same, I take a two different groups where G is equal to we have a set under addition, and G1 is equal to we have to take a set of a even integer, and then map defined is a phi of mn. So we take a, again we say this is clearly is a homomorphism. Why is homomorphism? We take a m or n are the element of set of integer, and then we have to m plus n is also set of integer because of a under addition this is a group. So if this is the element of this, then this can be written as a phi of m plus n is equal to 2 times of m plus n, and now this can be the same as a 2m plus 2n, and now if m is the element of a z, then phi of m is equal to 2n by the property phi is defined from z to this, and then similarly we have a n is the element of a z, so we have a clearly say that phi of n is equal to 2n, and then this is nothing but equal to we have a phi of m plus phi of n, and then we have to show that this also satisfy the homogeneity condition. So clearly we can say that if any map from z to 2z is defined, is a, again is a satisfy this condition. So this means clearly this is a homomorphism example. Okay, so now we have to move one more example, and that is a different. We have to take a phi is equal to x square from r star the set of real number under the multiplication into itself, and means we have to phi is defined from r star to r star. R star is the set of all the collection of all the real number non-zero real number. So or the real number. Now if we have a defined, and the map is defined the form of this phi of x is equal to x square for all x is the element of a r star. And now this is a group under multiplication, so we take any two elements, for example x and y are the element of a R star, then by the property of this we can say that f of x is equal to x square, f of y is equal to y square. And now if you have to just check is this, we have a x and y are the element of a two real non-zero real number, then this clearly x composition under multiplication, this is composition is multiplication. So we can say that x into y is also the element of a non-zero real number, and then we have to say that f of x into y is the same as a x into y ka whole square. And then you know that the set of non-zero real number under multiplication is a abelian group, and then by the abelian group property a b ka square is the same as a square b square, and then this is can be written in the form of a x square y square, and then by this x square is equal to, you have a phi of x and this is phi of y. So we again show that a set of non-zero real number under multiplication is abelian group, and is abelian group, then the property of abelian group is saying that a b ka whole square is the same as a square and b square. So by using this property we can easily say that this phi of x y is equal to phi of x into phi of y. So in this case also we say that this is a clearly is a homomorphism in this case also. Okay, so this is we have to complete. Now I just define some different way, the same thing. I just take a set of a real number, and then map is defined in the same in this form, and now we have to try to check is this homomorphism or not. If you take a x and two elements belongs to the set of real number, and this is under addition is a group, so you have a, this implies that x plus y is also the element of a real number. So this means phi of x plus y is the same as a x plus y ka whole square by the definition. And now if this can be the same as a, you can say that x square plus xy plus yx plus y square. And now if we take a phi of x is equal to, you have a x square, and phi of y is equal to, you have a y square. Now you see, if you have a phi of x under phi of y is equal to, you have a x square plus y square, and that is, this is clearly not equal to this quantity of a phi of x plus y. So in this case, if we have a, in place of a set of real non-zero real number, I take a set of all the real number, and under addition to, and map is defined in the form of a phi of x is equal to x square for any x belongs to R, is clearly is not a homomorphism, because of, we have to show that f phi of x plus y is not the same as a phi of x plus phi of a. So this means this is the one of the example which we show that this is clearly is not an the homomorphism in this case. Okay, so let's try some more examples. I take a this let z be the group of integers under addition, and this zn plus 1 is a finite group under of addition modulo n, and then we have a group of integer modulo n, then phi is defined the form of this x, then phi is homomorphism. Why is phi is homomorphism? Because you can just take it in the form of this phi of x plus y is equal to phi of x plus y, and this equivalence class of a we know that the equivalence class of x plus y is the same as a equivalence class of a x plus equivalence class of a y. So this we have to define into this form, and be using this addition modulo under this, so we can say that this is the same as a phi of x and phi of y. So this means we have to, for all x mapping into this form, so this is clearly, this is a, again is a homomorphism. Okay, so now I just another very interesting example of the general linear group. You know that this GL and R is a general linear group of n by n invertible matrices, and then phi of n is we have to take this map phi from GL and R to R star. R star is all the set of all non-zero real numbers, and then we have to define this phi of A in the form of a determinant of A for all A is the element of a GL and R. And now if we have to show that we take A and B are two invertible matrices of GL and R, and we try to show that this A and B are a function phi from GL and R to set of all non-zero real number is a homomorphism. So we take any two elements A, B belongs to A and B are the element of GL and R. If A and B both are the element of GL and R, then clearly we know that the determinant of A is not equal to 0 and determinant of a B is also not equal to 0. And you just say that we have to also define the form of this map is defined form if A is equal to same as a determinant of A and f of B is the same as a determinant of a B. Now this is a group under multiplication and this is also a group under multiplication. Both the groups are under multiplication. So we take a phi of A into B, and you know that this can be written as a determinant of A into B, and now by the property of determinant you can say right as A into B, and by the property of a determinant we can write determinant of A into determinant of a B. And now you know if this A and B are the element of a this, so then clearly we know that if A is the element of a GL and R, then by the definition phi of A is the same as the determinant of A, and phi of B is also the if B also is the element of a determinant of a B. So this is the element of a, this can be same as a, you have a phi of A and this is same as a phi of B. Then we can show that if any map from phi defined from GL and R to set of all non-zero real number by phi A is the same as the determinant of A for all A is the element of a GL and R, and then clearly it satisfies the property of a homomorphism. That means phi of A into B is the same as a phi of A into phi of B. So clearly this is again one of the example which show that this is a homomorphism. Okay, so now I just take a one more example, and then this is naturally is a question saying that we have a Z12. You know that this Z12 under addition modulo 12 is a group, and we take a Z10 and that is a under modulo 10 is a group, and we have a phi from Z12 to Z10, and this we have to define in the form of a phi of x is equal to 3x form. Now this means we clearly know that this x is the element of a for every x of the element of a Z12. So if this is the element of a Z12, then you can set it in the form of 3 times of a element of a Z12. You know that the Z12's element is equal to, you have a 0, 1, 2 up to 11, and then this phi of x element is a element of a Z10. Also you know that the 0 2 you have a 9. Now for example we have to take a for phi of 6, for example x is equal to, we have a take a 6, phi of 6 can be written as a 3 into 6, 18, and then by this is the under modulo 10. So we just calculate into this form, we take a phi of 2 is equal to 6, phi of 2 clearly 3 into 2 is equal to 6, and then phi of 10 is equal to 3 into 10 is equal to, you have a 30, and the 30 is under this is clearly congruent to 0 mod of 10. Okay, so this means phi of 10 is clearly we have a 0, and then phi of 2 is equal to, we have a 6. Now we have to take a phi of 2 plus 10, and that is equal to same as a phi of 12, and this is the same as a phi of 0, and now the phi of 0 is equal to 0, because 3 into 0 is equal to 0. So phi of this is equal to, you have a phi of 2 plus 10 is equal to, you have a 0, and now we have to take the other one. We have a phi of 2 is equal to 6, phi of 10 is equal to 0. So we have a phi of 2 plus phi of 10, and that is equal to 6 plus 0 is equal to, you have a 6, and clearly this is equal to, you have a phi of 2 plus phi of 10 is equal to, you have a 6, but in Z12 2 plus 10 is equal to 12 0, and then phi of 2 plus 10 is equal to phi of 0, and now you know that the phi of 0 is equal to 0. So phi of 0 is equal to 0. So clearly if we just see that phi of this is equal to, you have a phi of 2 plus 10 is equal to 0, and this is equal to clearly 2 plus 6 is equal to 6, then 0 is not equal to 6. So we can simply say that in this case that this is not satisfy the condition of homomorphism. So we can simply say that this phi is cannot be a homomorphism if we have to define a map phi from Z12 to Z10 by the mapping of a this. Not necessary, thus you can take any other element. We can try one more for this, verifying in this form. So in place of a 2 you have take a 4. If you take a phi of 4, phi of 4 if you take it is equal to 3 into 4 is equal to 12, and then 12, so phi of 4 is equal to 12, and 12 under 10 is equal to 2, so this is equal to congruent to 2 and mod of 10, and then you have to take a, suppose we have to taking the same element, this is equal to phi of and 5, and then you have a phi of 5 is equal to 15, 5 is equal to 15, and that is congruent to 5 mod of 10. So this you have a phi of 4 plus phi of 5 is equal to, you have a 2 plus 5 is equal to 7, and you have a phi of you have a 4 plus 5 is equal to 9, phi of 9 is equal to, you have a 3 into 9, 27, that is equal to, you have a and equal to 7. But in this case you can see if we take these two elements, we can show that this is satisfy this condition, but it is not true for each and every elements of this set. So that's why we can say that this is clearly is not a homomorphism. So we find certain element, we take a 4 and 5, under 4 and 5, 4 and 5, that is showing that these are the same, but when we take a different this set, phi is equal to phi 2 and phi 10, and then 2 plus 10 is equal to this does not satisfy the condition of a homogeneity. So this means we can simply say that in this case this is set is a clearly function phi from Z12 to Z10 defined by phi x is equal to 3x clearly is not a homomorphism. So now I just give you the brief about the this definition, and then we try to discuss various example of the homomorphism. We have to show the trivially homomorphism, and some other example where we show that the these are homomorphism are is homomorphism, but some of the example I show that that is not a homomorphism. This last one is and another we have to take a set of real number of x non-zero real number x to the power fx is equal to x to the power 2 under addition, a set of real number under addition we have to take him. Phi of x is equal to x square is not a, again is not a binary operation. So now I just stop today lecture here, and we try to continue some more examples in the next class, and also try to discuss some elementary properties and some more definition of a homomorphism or different types of a homomorphism. We have to show that if the function is homomorphism, one is called is epimorphism, but is called is a monomorphism, and also the isomorphism. So now thank you very much for today.